Hi, everyone. I'm still getting used to that impressive demo video in the beginning. It's so cool and so loud. I feel like I'm in some sci-fi movie. I think this is a great update this year at DevOps. My name is Alina. I'm a developer advocate for GraalVM at Oracle, and I'm here to talk to you about all things GraalVM. This will be a deep dive. This will be 3 hours, and most of them, I would say 95% content, will be focused on native image, so the ahead-of-time compilation part of GraalVM, and then we'll touch a little bit on languages and other updates towards the end of the talk. And before I get into any details, I would like to say a few words about the project in general. Oh, let me adjust my mic. I think this is fine. Yes? No? Sorry. Am I too loud? No. As you can tell, guys, this is live running in production, so some disruptances might be expected, especially if I touch my mic. Should I remove the earrings? No. OK, we have the blessing from the AV team. Yeah, thank you. So what I was saying is I would like to also say a few words about GraalVM and the project as a whole, what are we working on now, and what we'll be doing moving forward. A few weeks ago, on September 16th, we have released our GraalVM 25 release. That went out right on schedule, and we have released it in both editions that we have, GraalVM CE Community Edition Open Source, and Oracle GraalVM licensed under GFTC. That is quite permissive license that allows free use in production for a very wide range of use cases. And yes, you can already get those from SDK from our website and keep using whatever component of GraalVM that you like. And moving forward, we have 2 big goals. We will continue working on native image. Native image is very important for us, for our partners in the community, for many Java frameworks that use native image as a platform. And I hope it is also equally important for you since you are in this room. And another big direction of our work will be the language runtimes. So particularly, this will be for Python, JavaScript, and WebAssembly. Those are the languages where we see a lot of interest from our community. And we plan to expand our efforts in those languages moving forward, whether you want to make them usable from your JVM applications embedded, or if you just want to run plain Python, JavaScript, WebAssembly on our runtimes. And we have a lot of great features and many ambitious projects that we want to accomplish in the next few months and years. And the second part of this deep dive, I want to talk exclusively about GraalVM 25 and new features that we have released in 25, and also give you a preview of our projects that we will work on moving forward that are not fully implemented yet, but we have some very cool things to show. So make sure to come back for the second half. That's where you will hear everything about the new and the most recent changes in GraalVM. With that, I will sit down so it's easier for me to do all the demos. And you can see from the screen that we will not be doing any slides today because I want to show you as many demos as possible. So my plan will be to go with you through this agenda that we see on the screen. And then for each bullet point, we will see a demo so that you can see how all those features can be used in practice. And a very quick intro. I don't think I need to introduce GraalVM anymore, but just so we have the same language and we are at the same point. So GraalVM has a big, great JIT compiler, GraalVM JIT compiler, the best JIT out there, if you ask me. It's a compiler itself written in Java. So many people will tell you, or some people will tell you, that Java is maybe not their first language choice for something as level as a compiler. But what's cool, we are using our own native image, our ahead-of-time compilation, to compile that Java compiler to a native executable itself. Then the second part is native image. That's our ahead-of-time compilation, where we take your Java application and compile it ahead of time into a native executable. And we have 2 ideas there. One is to produce a native executable that contains everything that you need, and only the things that you need, so you can deploy it as is. Maybe even on a system doesn't have JVM on it, and it just fully runs as a native program, but you can still write your code as you always do. And the second part of that idea behind native image is to give you a way to shift all that work to the build time, because we believe that many applications are started more often than they are built. So it makes sense to do all that overhead work around compiling, profiling, etc. at build time, and then don't have to repeat it every time you start your application. And then the last big part of GraalVM, why we are sometimes called a Polyglot VM, is that we can execute all those other languages with a primary focus on the ones that I have mentioned in the beginning. So Python, JavaScript, and WebAssembly, whether embedded in your JVM applications or just plain execution of each of those individual languages. And with that, let's go ahead and dive into our first demo. And to start, I would like to migrate an existing application to GraalVM and native image. And our example application will be Spring Petclinic. So this is the most standard, normal Spring Petclinic app straight from the Spring team and Spring community. As I was looking at it, you might also notice that there are some familiar names and faces here among contributors. You can see Stefan, you can see Patrick, Brian, Sebastian. So this is the most standard Petclinic application ever. And I think many speakers like using this application because this is a quite standard reference point for like benchmarking and measuring various aspects of Java and namely Spring Boot applications. So speakers love it, but I'm wondering how many of you have tried building Petclinic or it's not something that you have done? OK, I see some hands, but yeah, it seems like you probably built more your own applications rather than playing with the capabilities of Petclinic. But let's go ahead and get this one. And let's get ourselves a terminal. And to begin with, I'm running on GraalVM 25. So this is my GraalVM version. And yeah, the latest release with all the cool updates and performance updates and all the things that I will mention in the second part. But let's go ahead and get our application. So git clone our Petclinic. And let's go and take a look. Now, I don't think it needs many introductions. I imagine even many speakers at this conference will show you Petclinic. But just to very quickly go through it, let's maybe look inside. And it's a pretty standard reference Spring application for modeling those more enterprisey web kind of deployments where you have your pets, your owners, and it emulates a work of a Petclinic where you can schedule visits for those pets. You have a list of owners and pets that you can read from a database. And then to schedule those visits, you write them in a database. So pretty standard stuff. And then when we look in our POM XML, what we see here is, again, all the standard Spring things, a more or less recent version. We see our dependencies around data, web, validation, timely for templates. And the part that is interesting for me is this native Maven plugin. So as you can see from the coordinates, this is coming from our team. So the project is identical to what you would generate at starterspring.io and add native image. And the Spring team and many framework teams out there are nice enough to add our plugin as a way to compile native image applications and as a standard interface into all things native image. So let's go ahead and let's compile this one. OK, we have started compiling. And the first tip that I would like to give you here, as I want to make this talk a bit more practical and share the things that I think you should use if you are developing applications with GraalVM. I'm building application as is because I want to show you the most sort of vanilla, simple journey to the production deployment. But back at home, and I strongly recommend that you would do it too, I would do the following. So here for the native image plugin, I would add a configuration block. And here, the syntax to add more commands would be to add more build arcs. And within that, you can start adding individual build arcs. So build arc. And namely, what I would do is I would start with this -ob flag. So this would give me faster builds. And there is no magic behind it. The way this flag works is just doesn't optimize application fully for peak throughput. So this is your way of telling native image, I'm not deploying this application yet. I'm just building it to see that it works. Maybe I just introduce some changes and I want to make sure that it's still functional. And I don't need to optimize for production. I don't care about speed. I just want to get my build back to me as fast as possible so I can validate my assumptions. Better yet, what you can do, and what I sometimes do, is you can wrap it in a Maven profile and call it something like dev. And there you can have quick build mode because you're still developing your application. And along with this, you can add some other tooling that you might use as you're developing your application. So later on, we will talk about build reports and how you can deeply analyze your builds. So for example, in that Maven dev profile, you can have a quick build mode and a build report that will help you analyze and compare your builds across the time and across many different builds. But for now, let's keep it as is, so you don't tell me that I specifically for the conference, cheated and created some fast build. But this is genuinely an advice that I would give to you as you are developing your application. Add the -ob flag, and then when you're ready to move to production, either remove that flag, and then you will trust the default heuristics in native image to optimize for peak throughput, or you can explicitly specify -02 for reasonable performance or -03 for peak performance. And that is what you normally would want to have in production, optimized for full speed. In the meantime, my application is currently compiling. So again, this is a full sort of production build, right, with all the optimizations in place. And as it compiles, we can see the information that it had detected inside my application. And for example, it says that as it's analyzing the application, it has found that there are almost 40K types and almost, where are the methods, 100,000 methods in my applications that are found reachable. So what does reachable means? Reachable means that they were reached during the analysis. So the way we are able to optimize and compile application ahead of time is that we perform a very complicated, sophisticated analysis, and we try to find everything that your application needs across your user code, your dependencies, and your JDK, and then only put those things that you actually need into that native executable. And this way, we can strip away all the execution infrastructure, the JIT compiler, etc., and you only have your native executable. But obviously, for this to happen ahead of time, before the runtime happened, it needs to have some sort of way of enabling this, and our way is a closed world assumption. So to build the application before the runtime happened, we need to understand everything there is to know about your application. So this happens under closed world assumption because the actual runtime hasn't happened yet. So whatever native image needs to do for you, it can be pretty much anything as long as you instructed at the build time what needs to be available. I configure things that need to be available at runtime. So as I was talking, this application has compiled in 2 minutes. We can see some random extra files here, primarily courtesy of AWT that being pulled by some dependencies. But what we actually need is this one, Spring Petclinic, where it says executable. And the overall compilation time has been 2 minutes, which I would say it's not too bad. And then if I had that -ob quick build mode, it would have been maybe 1 minute, 30 seconds. So honestly, I think it gotten way better over the time, specifically the build time. Now, let's see it in action. So it's target Spring Petclinic. And it starts, we can already notice quite fast in 200 milliseconds. And when we go and look at the application, localhost 8080, my port mappings, OK. OK, let's try again. This is a lot of ports. So this is running on a Linux cloud instance. So hopefully we can have like a sanitized, isolated environment that is not being messed up with by my local machine and by anything that is going on with the screen sharing and everything. But why do you not want to respond? OK. Not sure what happened there, but here we are. It has been up. It's just, I guess it was something with either with the internet or with mapping to my local laptop. But we arrived there all good. And the functionality inside is that you can find owners, add owners, you can explore existing ones, you can retrieve the database of your veterinarians. So it starts, I think we can all agree, quite fast in 200 milliseconds if we spare the time it took to propagate to my local machine for the sake of the demo. And if you have ever heard anything at all about native image, you might have heard that people tell you that it's really good for startup times. So let's see if we can compare this with executing on the JVM. And as my JVM, you've seen that I'm running on GraalVM 25, so our JVM moving forward will always be GraalVM. So let's run it on the JVM, and let's compare what we can retrieve from those two applications. First of all, I would like to time, specifically on this machine, what are the characteristics of my process, so how much memory it occupies, how much CPU it uses, etc. So I will use the Linux time command, and I will ask it for a longer output so we can compare those things together. And then I will start my application. And here, as you can see, I'm starting specifically my jar with the Java jar command. What happened? Okay, Spring Petclinic dash. Oh, is it verbose? Yes. Sorry, this is between Mac and Linux. I'm getting confused. Not long, but verbose. This is it. So this has started our Spring Petclinic. Let me see if we still see it locally or if it does not propagate here. Localhost 8080. OK, we are up. It's functional. And let's click around a little bit so we can give the application something to do so it's not entirely idle. So we have emulated some user activity. And down the line, we will also do a nice heavy benchmarking to see more of how both applications perform under load. So let's kill it. And this time command gave us some info on the performance characteristics of our process. And now let's go ahead and do the same. So we will use our time command. Only this time we will time our native image executable. So target Spring Petclinic. And previously, I was running with Java jar, because sometimes when you run from the Maven command, such as Maven Spring Boot Run or whatever is the framework that you use, sometimes frameworks can do additional tricks around startup to give you a better developer experience. And I appreciate it as I'm developing applications, but specifically for such performances comparisons, I would like to have more control over what's being run. So it's always a bit more sort of comfortable for me to run a jar, because I know exactly the command that is being executed as opposed to the Maven run command. So now we have started our native application, and we can try clicking around again. Localhost 8080. It's up. It's quite snappy. And again, we clicked around and we did some user sort of activity. And now let's compare what we see. So this first run was our JVM. And first, I would like to analyze what we see in terms of CPU. So we got 80% of CPU that has been used by this job. Granted, the application is not that large. It's a couple of templates, controllers, etc. But still, I would say it is some CPU that is being used, especially if you're maybe deploying to a cloud environment where you actually pay for all that infrastructure that you are using. As we compared with native image, even though I clicked around trying to give it some sort of load, the performance of the amount of CPU that we were used is so low that the system cannot even detect it properly. It shows at 0. It can be somewhere around 0 to 1 to 2%, depending how long you kind of click and give it a load. But the point being that even for this small application, the CPU use is so small that the system cannot even see it. So we can imagine that this could have been maybe like 1%, and it's still much lower than those 80% that we had on the JVM, because as we all know, JVM has a lot of great capabilities when it comes to peak performance. But to arrive there, when your application starts, there is quite a bit of work to be done. So it needs to look at your project. It needs to load all the classes. It needs to look at what classes are warm, which methods are often executed, which loops are often executed, collect all that information. And as it does so, it does spend some of that CPU and memory to perform all those tasks. And speaking of memory, let's also compare the memory use of both processes. So here we are on the JVM, and this is, let's say, roughly 760-ish megs of RAM that the JVM is using. Now, granted, in this simple comparison, we will not change in the memory requirements. We are not setting any XMX settings. But I would say this is still some memory to be used for a fairly trivial application that we have seen. So let's remember around 760-ish megs. And then native image in comparison here is using below 200 megs. And in general, I think this is a good benchmark and a good comparison, because if you ask me, and sometimes users do ask this, what are exactly the savings I can expect from native image? It's always hard to give a generic answer, and I don't like doing this. But on average, you can expect around 3x performance improvement around memory usage with native image as opposed to the JVM. And it comes from the fact that we did all that work that the JVM normally does at runtime. We did it as we were building the application. So we compiled it, we optimized it, and then when it starts immediately with compiled, optimized machine code, and also with a pre-populated heap. So not only you prepare your code, but also whenever possible, we try to populate the objects in your heap, so you don't need to spend time and precious resources on that. And speaking about memory, I would like to show you one more example of how this is working in practice, and one of the users of GraalVM and native image, namely who have used native image for those benefits. So let's look at that user use case. OK, so the user that I want to mention will be, actually, maybe I can just retrieve from here. The user will be Disney Streaming. They have published this very nice blog post that I really like on the AWS blog post, where they were talking about how they were improving developer productivity, but also specifically improving cold startup times of their applications deployed on AWS Lambda. And namely, this is the messaging team at Disney Streaming, the team that is responsible for sending all those notifications that we get as users, so push notifications, email, etc. And as you can imagine, that it's a quite high-load system. There are tons of notifications appearing all the time that need to be sent to the users. And to me, it also looks like a very good use case for something like serverless, where there is a specific event that triggers that notification that needs to be sent to a user. And they're talking about how they were approaching cold start times for their Java applications. And first, they were approaching it by adding more and more memory to their Lambda deployments. And they managed to cut those cold start times by 2x, I would say, by increasing the memory that they give from 512 megs to 3 gigs. So I would say this is a good improvement. They went down almost by 2x, but it did require a little more memory to be added. And this was still on the JVM world. And then they wanted to try something new. So the application was a Micrometer application, and it was quite easy to move it to native image. So when they moved it to native image, they have arrived here at this second chart. So this is still AWS Lambda, and still they compared across various deployments with various memory allocated to the workloads. And what you see here, the blue one is Java, and the red bars are native image. And again, the same story, they added more and more memory, and what they observed is a similar trend where as you add more memory, the startup times improve as expected. But then with native image, even at 512 megs, I think this looks like a pretty decent startup times. And then if you can afford and you want to give even more memory to have the best startup times possible for this given workload, they have arrived at 83 milliseconds, which I think is pretty good and a very good improvement. So overall, they talk in this blog post about how they are quite happy about those startup times. And I don't think they talk about any sort of cost implications in this blog post, but normally in the cloud, you can also assume that if you are using resources for less time, so if you're not spending that much time occupying those resources, it's also, I think, reasonable to assume that you can reduce that cloud cost because you're not occupying that memory for that long. Your whole workload just finishes much faster. And I think this is a very important benefit of native image. People always tell you that native image is great for startup time, for packaging size. But I would argue that resources efficiency is even more important, whether you run on your own infrastructure or in the cloud, or in general you want to reduce using unnecessary resources. A native image could be a good way to accomplish it. So this blog post, I will link to it from the repo that I'm showing you today. And if you want to dive deeper into this example, you can do so. Now, We talked about how we migrated our friend Spring Petclinic to native image, and there our journey was very smooth because Spring put our native Maven plugin into POM.xml, and all I needed to do is just compile the application, and it worked. But what if you have some application at work that you want to move to native image and you're not exactly sure where to start? So let's go through the steps there, and those will be our steps to make it happen. So this is the section on migrating applications and using libraries. Before we dive into the specifics of using libraries, the #1 step that I would like you to encourage to do if you want to migrate an existing application to native image is to either look at your framework and see what kind of support they offer to native image. So all the major frameworks out there, Quarkus, Micronaut, Spring Boot, they all offer support for native image out of the box. But if you are unsure, or maybe you're having some internal framework, or if you have some application where framework does not support native image somehow, I would recommend that you start by getting our native build tools. And native build tools is the set of plugins developed by our team. You can choose Maven or Gradle plugin, whatever it is that you prefer. That will help you build, test, and most importantly, work with libraries when you're building applications with GraalVM native image. So if I had to move an application that does not contain this plugin yet, my #1 step would be to add it, and then from here, I will get a lot of assistance, and I will get a nice interface to configure applications to work with native image. I'm a Maven person. I prefer Maven much more. But if you are a Gradle person, we have the exact same one for Gradle. You can just choose whatever you like. So, OK, we have our plugin, and obviously we know that all the libraries in your project are also very important. So how do you work with libraries in GraalVM native image? And when I talk about libraries, or when someone else talks about libraries in native image and they mention some sort of incompatibility or issues or challenges, normally there is #1 suspect in that regard, and that #1 suspect is reflection. So people sometimes will tell you that GraalVM does not support reflection. I'm wondering if you have heard this, or do you hear this still, that GraalVM does not support reflection? Still some hands, but luckily not as many. In the beginning, when we were starting to do this, like half of the room would raise their hands. What's the story with GraalVM and reflection? So we do support reflection. On GraalVM JIT, no problem whatsoever. And even in native image, we support reflection out of the box. But reflection is very dynamic in its nature, right? So it's resolved at runtime. And as we know, in the native image world, technically, at the moment, runtime hasn't happened yet. That's why reflection and its friends, such as serialization, proxies, etc., they require additional configuration. Configuration being that you need to tell it at the build time in the format of configuration files, JSON, which of those calls need to happen at runtime. And this might sound scary, some configuration, some JSON files, but I believe right now in 2025, this is a solved problem. And this section here will talk about how you can use libraries with native image and why I think this is a solved problem now. So I will use here sort of interchangeably reflection and using libraries, because normally if there is a challenge with a library, most of the cases it will be reflection that needed to be configured. So how do we make libraries and libraries that heavily rely on reflection work in native image? #1 thing is we have basic sort of predictable reflection calls support in native image. So things like class for name, etc., that are possible to reason about at build time, native image can figure out of the box. So limited, but out of the box reflection support exists in native image as is. But what if there is something else? So beyond that basic support in native image, how do you make libraries work if they are using reflection? The #1 thing, this would be sort of a newer trend, but I see more and more of it lately, is that a library might be designed to be native image friendly and not relying so heavily on reflection out of the box. And this is certainly a new trend, but I see more and more of those libraries appear. And one benefit is clearly native image and native image compilation. But another benefit is that reflection, as powerful and useful as it is, it can add a bit of, let's say, overhead to your application and some other concerns and considerations. So it's nice to see that some libraries are totally possible to design from the ground up, not relying as heavily on reflection. Now, if that is not the case, and we understand that many libraries existed long before native image arrived and came to be popular, how to make those existing libraries work with native image? And the first example that I want to show here for that is H2. And in H2, in the past, I used to show a demo where I had an H2 application, and I was building it, and it was failing. It was building successfully, but failing at runtime because it could not figure out how to work with some of the reflection calls in native image. But now I don't need to do it anymore because here we are looking at the source code of H2 itself. And in the source code, we see those configuration files for native image. So this one instructs native image what to do in terms of reflection, which classes, fields, etc. to make available at runtime for native image applications. And similarly here we have a resources config JSON where we see the grand total of one resource configured to be working with native image at runtime. And if you happen to be a library maintainer or if you know a library maintainer and you want to add support for native image, the best way to do so will be to embed this configuration in the library. This is the easiest path for your users, and this is the best way to ensure that your application compiles and works as it should with native image. But again, we understand that all libraries have a lot of user requests. A lot of open source teams are very busy. We are also an open source team, and we also have a huge backlog of things that we want to implement, but it's not always so easy to get to all of them. So we understand that not all libraries can do this immediately at the moment. So the best thing if a library cannot include this config in the source code would be, imagine if there existed something like Maven Central, sort of, but for native image configuration. Because maybe if I have figured out a configuration for some library, let's say MySQL Java connector, maybe a person next to me doesn't need to do the same thing because I already solved it for my application for that particular library. So we thought the same thing, and we have created together with our team and community this Reachability repo on GitHub. And this is that sort of Maven Central, but for native image configuration. So it's a community project. You will see here among contributors a lot of people from our team, but also people from Spring Boot, from the Micrometer team, etc., all contributing here to make those libraries fully compatible with native image. And inside, we see a lot of different things, which are all those popular libraries in the Java space. And each folder here contains config for a specific version of that library for native image. And the best thing is that this is fully integrated with our native build tools, native Maven and Gradle plugins. That's why I was telling you that if you want to get started with GraalVM native image, number one step will be to add our plugins, because our plugins will analyze your project, look at your dependencies, and come here to pull config for your dependencies from this centralized repo. So if you are using that specific Kafka client, the configuration will just appear for you. You don't need to touch anything. And what's interesting, I was here at DevOps last year, and there was a library maintainer talking about how they implemented support for native image to their library and how they contributed this metadata to this repository to make it usable and available to their users. But as a library, honestly, the preferred way is to get it inside the library itself. This repo might be a bit more popular. That's why people contribute metadata here, because they know about it, and this is like a public reference point. But the best way is to contribute to the source code of your library. And this goes as far as sometimes people look here for the libraries to evaluate whether or not their project will work correctly with native image before they compile it. But this is not the complete information, so this is only config available here. If you want to very quickly evaluate whether your project will compile, what I would recommend doing is I would recommend you go to this page on our website. And here it's called Frameworks Ready for Native Image, and also Libraries and Frameworks Ready for Native Image. And here you will find a very, very long list of various libraries and frameworks and the level of support that they have for native image. So this might look a little bit confusing, but long story short is if your library is here, it's a good sign. So let's say I'm looking for my MySQL artifacts and I have them here. And the stars here, this is just to denominate how come that support is available. So 1 star means this is supported through the Reachability repo. That config is available here. And 2 stars is what we recommend is that maintainers embed the configuration for better developer experience. So if you want to very quickly evaluate whether your project will work with native image, I would recommend that you come here and you analyze your dependencies here. And this is the most complete source of libraries that are known to be testing and integrating with native image. Now, this was about making configuration happen either through the Reachability repo or through the source code. Now, we have some very cool updates in 25. I will talk about this in the second half of the talk, but basically we're introducing this completely new way of building native image applications where you don't need any configuration at all. You can just instruct native image to pull your project completely. So not strip away anything, but include everything or a specific part of your project, such as a package or module. So if you have a problematic library, it's not a problem anymore because it can be pulled completely. And then we also have some good tooling and ideas of how you can optimize the size of that image so that you can still have a smaller image and you don't need to keep everything around. I think this will be extremely useful, and in the second part of the talk, we will talk about it in more detail. Now, let's talk about other use cases. So I genuinely believe, and I'm not just saying this because I work on GraalVM, but in the year of 2025, if you're working on a new project with GraalVM, you will have that config coming from somewhere here. You don't need to worry about configuration. So I don't even get that many library questions anymore. Most of them seem to be solved or will be solved by using this preserve mode. But let's say you are in a bit less fortunate scenario where you have some application that is not working with native image yet. Maybe it's some old legacy application with older versions of dependencies, or maybe you have some internal dependencies at your company where there is no community support for native image configuration. So how you can make that happen? And we are getting a bit into the woods here, but just bear with me for like 5 more minutes in this section because I think this is important. So number one thing is if you want to make some of your user code working with native image and you're not entirely sure how, what you can do is you can check in your framework support what kind of support they offer for native image and reflection and configuration. So here we will, for a change, look at a Micrometer application. And here we have this reflection controller that is doing a bit of a confusing reflection call to not let native image to figure out this out of the box. And the call needs to end up here in the message class and message field. So because I'm on Micronaut, which supports native image out of the box since day 1, I can just use their annotation that is called reflective access. And what this will do as a package my application, it will programmatically generate that config for native image for me. Here on the classes meta-inf, it will generate classes that will instruct native image how to handle that reflection call. So if you have a framework that supports native image, look at how they help you programmatically generate config for native image. So this is one thing. The next one is, let's say you don't even have framework support, so you just have an old application, but you really want to make it work with native image. What you can do in that case? In that case, even if you have 0 support from the community or frameworks, you still have options. And that is native image ships with this native image agent that can observe your application behavior on the JVM and automatically or semi-automatically produce that config for you. So clearly, it's not very exciting to write JSON files. That's why we have automated this part, and you can use this agent to produce the config. Now, I'm always asked to tell you that this is not a silver bullet. Please check the information after the agent, see if it's complete. But from my experience and from the experience of library maintainers, this solves around 90% of library configuration just by running on the JVM with the agent. And then the last point into making libraries work and in general simplify your developer experience with native image, we have a new amazing project that I'm a big fan of that is called Crema. That will make even more applications work with native image out of the box by lifting some of our closed world assumptions and limitations. This is very cool. I'm very excited about this one. I will talk about it again more in the second half. So with that, I would like to switch to the performance optimizations part and talk about how you can optimize the performance of your native image, but also what are the different targets that you can have when it comes to optimizing your application's performance and its various characteristics. So on the compiler level, there are several things that you can specify for native image, and namely our compiler to follow. One is you can instruct the compiler to not do any optimizations at all. And this will be the most useful if you want to debug, and you want to debug specifically native image. Maybe you don't want the compiler to modify your code significantly, so you can instruct it not to do any optimizations. Then -01 is a similar one, but just basic optimizations, but you can still perform your debugging on this level. And then 1 going through 3 is just increasingly adding more and more optimizations, with -03 being the top level. So if you don't want to perform any manual sort of optimization that I will show you next, I would highly encourage you to at least remember this one flag, -03, and this instructs native image to apply all the optimizations that it can on the compiler level to optimize your application for the best peak throughput. And also, I think those are easy to remember. We are following some common sort of compiler conventions here. So the -0 through 0 to 3 are the optimization levels. Then you can optimize for the build time, what I mentioned in the beginning. As you are developing your application, maybe you don't need the full peak throughput yet, but you want to get the build fast so you can see that application still works and compiles and everything works as expected. One more interesting one is optimize for size. I cannot say that for me personally, this is something I use often, but I see it being often used by authors of projects like CLI application, where you want the application to be the smallest, or if you are building native images for distribution, this -OS can be useful for you there. And then PGO is PGO will be optimized on your application for the best peak throughput with profile guided optimizations. And also under the hood, it triggers -03. So PGO will be the best peak throughput coming from the compiler, but it will need a little bit of work from your side. So those were base optimization levels. And now let's take our Petclinic application for some performance benchmarking, and let's see them in action. So for that, I have my Spring Petclinic additionally set up with my benchmarking script so I can go faster. And here we are. So our benchmarking setup will look the following. So as a baseline, we will be using JIT. I think it always makes sense to compare to JIT, as JIT is, most people's normal mode of execution. So first, we will run our Petclinic on the JIT, and our JIT will be GraalJIT. As I said, I think the best JIT out there, so you cannot say that this is, not a good comparison baseline. And we will start our application with memory settings set to 512 megs. We use the tool called PS Record to observe the performance of our process around our resources usage. So we will measure our memory and CPU usage. And then the benchmark will be designed in a way that we give it 10 seconds to start. So not even touching the application, but we just give it a chance to do all that housekeeping work. And then we will warm up for 20 seconds. So we will send requests, but we will give the JVM a chance to look at those requests, look at what methods become hot and optimize. But we will disregard, throw away those results because we want to give a chance to warm up. And then for 20 more seconds, we will do the actual benchmarking round where it properly started, it's warmed up, and then we can benchmark. So this will take a while, and this is still not entirely scientific benchmarking. But for the sort of conference setting, I would say this is fairly decent for the sake of saving time, but still doing some reasonable work. And I talk about the methodology, but what are the actual requests that we are sending to our application? This is something I'm actually quite proud of, because instead of starting our application and just bombing the home endpoint with like million requests, we are trying to be smarter. So we are trying to execute many different code paths. And for that, we are using this request script defined in Lua, where we are creating new paths, creating visits for those paths, retrieving info on owner, retrieving info on the visits. So we are almost trying to emulate a real human being clicking around different endpoints, so the application is not overly optimized just for the home endpoint. And as I was talking, our application has finished running. And the results that we can observe are that during the warming up round, we got the throughput of 556 requests per second. And then as it properly warmed up, it arrived at 1,000 requests per second. So do you think this is fast or not? You can just shout out. Yes. OK, I also think this is fast. But let's see if native image can do a comparable job. For native image, we will do something very similar, where we will start a native image application with the exact same settings. It also waits for 10 seconds, although honestly, it doesn't need to. We will see later on the charts that this time was not needed to spend there waiting, but we just want to have completely equal comparison with the JVM. And then we do the same. We are starting, warming up, and then we are doing the benchmarking round. So let's run our native version of the application. So who thinks this will have a higher peak throughput? I like the faith that you have in me, but you also, I think you can agree with me that the JVM is amazing, and peak throughput is the JVM's strongest suit, right? So it's very hard to beat it at its own game. Let's see if we can. OK, we see our warming up round is finished, and it's 800 requests per second, which I think is not bad but for the warm up, but let's see if we can make any better. OK, now it's finished, and we see that the final peak throughput is, I would say, good. It's not too bad. Honestly, JIT did even a little bit better than it sometimes does. So 1K requests per second is a high bar. But native image, as we see, it arrived in the end at 832 requests per second. And yes, I think this is quite good, and a lot of work, honestly, can be done here in the warming up round as the JVM still warms up. So I would argue here, as we warm up, we already get more work done that maybe your application is even meant to do. But this is still not as good as the JVM. And you know me, if you've ever been to my talks, you know that I might still have other tricks that I want to show you. So let's run one more version of this application, and it's a very similar setup, where it's also a native image application, but it's native optimized. So it's built with a few additional optimizations in place. So what are those optimizations? Native image, probably the best, most powerful optimization that you can do in native image is PGO. It's profile-guided optimizations. I hope that by now, we did a lot of those talks, you have heard about it. But very quickly, what you can do with native image is you can build an instrumented image. So build it once with a PGO instrument flag, run it as an instrumented, and hit it with a relevant workload. And then when you shut down your application, it was observing what was happening and what was becoming warm as it ran. And it will produce for us profile files similar to what the JVM does as your application runs. So as your application runs, JVM looks at it all the time, and it's trying to find what parts of the application are most warm, where it makes sense to spend those compilation efforts for the best trade-off between effort spent and peak throughput. And with native image, we are doing something similar, only we are doing that in the native image world with an instrumented run. And you might tell me that, it's still not as dynamic as the JVM. The JVM adapts on the go. And it's all very true. The JVM really adapts on the go. But I would argue that with native image, PGO and profiling in general is in a way not worse, but just different from what the JVM does. Because one strong thing that native image has is that we are building your application under closed world assumption. So we are limiting the world. And this way we get a more full understanding of your application. Because for us, nothing unknown can happen at runtime. no new info technically can appear at runtime. So we can more fully profile and more heavily, aggressively optimize your application because we have more info of the complete picture. So it's not necessarily that one is better and the other is worse. It's just that they are very different. So we have built this application with PGO, and the other few pieces of performance optimizations that I would like to mention to you is one, you can use G1 GC, and in our benchmarks of most of the benchmarks, we see that G1 GC, if you want to target the best peak throughput, G1 GC would give you the best peak throughput with native image. We have other GC options available. We have recently added a new project where we will add a brand new GC in native image. But for the time being, and especially for like longer running high load workloads, G1 GC will give you the best peak throughput. And then a small flag, but still quite useful, is called mArc native. And this you also can add to your native image build if you want to have the best peak throughput. And this instructs native image to make the best use of the specific hardware features that it sees on the machine where we are built, instead of optimizing for a wide range of similar machines. So we do not do cross-platform compilation, as you might know. So I cannot compile on my local MacBook for my remote cloud instance, but I can instruct native image to specialize specifically for my, let's say, Apple Silicon M4 Pro, as opposed to some older models of a similar machine. So this gets you a few additional performance percentages improvement. Now let's compare the numbers. So the JVM was finishing at 1,000 requests per second, very good results. Sometimes you get around like 900 in this setup. Then the native image out of the box was finishing at 832. And native optimized, this also is a bit better than honestly I would expect, is at 1.1K requests per second. Now here, every reasonable, responsible speaker will tell you, please don't take benchmark results at a face value, always evaluate on your own workloads, just use it sort of as guidance, to never trust the numbers that you see someone else run. But my point here being is that if you do go this extra mile and you know which performance optimizations to apply, you can arrive at a very good performance with native image when it comes to peak throughput, in addition to the things that we have already discussed. So in addition to startup time, memory usage, packaging size, you can also have very good peak performance. And I understand that PGO requires a bit of work. So as I said, you need to build an instrumented image, run and hit it with a good workload, and then build again. And then I know some people who do not necessarily want to do this two-step process, but also they do not necessarily care about squeezing every last bit of performance out of a native image. So what can you do in that case? What if you don't want to have this two-step process, or what if you just want to have a very simple CI/CD where you can just do one build and have your native images deployed? Now, in that case, it seems like the work that we suggested that you do during the PGO could be a good candidate for ML automating it. And indeed, we have a little ML in native image, a little ML model that will analyze your application as we build it, so statically, and it will try to predict the performance profile of your application and then guide the compiler to optimize those specific parts of your application that we think will become hot at runtime. So clearly, this is not as precise as you giving us specific info on what you run and what became warm as you ran the application. But here with just one flag, and this is available in -03, you can have better peak throughput available out of the box. And this will give you, I would say, about 8% performance improvement over not having any profiles. So if you don't have any profiles for your application, you just run as is, but then you add this ML PGO in -03, you can expect around 8% performance improvement out of the box. And I would say that for no extra effort from your side, this is a very good improvement. Then for the next release of GraalVM, we have already work underway, which I think we will be able to merge and then ship with the next GraalVM release, where we are further improving this ML PGO with a context-sensitive version of it. And then I think we can arrive at maybe 10% performance improvement out of the box. So again, for ML, I think this is a quite good improvement to have if you do not provide any profile, if you just build one build with this -03 flag. Then also, when it comes to sort of performance and memory measurements, you can also manage the memory of native image, as you saw in my benchmark with XMX settings. This is also available to you in native image. And talking about performance, as our benchmark ran, we also did some measurements of all our 3 processes. So let's compare how our applications behaved as we were running the benchmark. So I always get questions, what is the tool, where this is coming from? So this is from PS Record. This is a Python tool that helps you observe a process and then produce those nice visual charts of your process. And let's compare. So this was our JIT, this was our native image out of the box, and this is our native optimized. OK. So what we are looking here is each of our benchmarks as we run them, JIT, native image, and native optimized. And the charts here are the following. So the horizontal blue line is the memory setting. And if you remember, we set it to 512 for all 3 workloads. So yeah, the JVM here went a little bit overboard as we hit it with additional workload. But native image had also 512 available, and it didn't even use it all. And then the red vertical lines are CPU usage, and this indicates for us how busy was our system, how many CPU resources it consumed. And specifically, it also gives us a timeline visualization of our benchmarking strategy, because we see that for the JVM, everywhere we gave 10 seconds to start. And for the JVM, we were quite busy for first 5 seconds, because then the JVM loads, it needs to load all your classes. But to be safe, we gave it 10 seconds, so just so it has time to prepare and be ready to accept requests. And then with native image, there is a tiny little spike in the beginning, but then it's just idle, and it waits for us to start getting some requests so it can start doing some reasonable work. And another observation that I have here is clearly CPU is less busy with native image, because as we discussed, the idea that we have with native image is to shift the work left to move more work to build time, so you don't need to repeat yourself again at runtime. But then with the JVM, it's, as we expect, a bit more busy because more code becomes hot and it needs to optimize that code. And my probably most interesting observation is around memory. So with the JVM, obviously, we are a bit more busy. We have more things to do, so memory usage is higher, even though the workload is the same. But all that extra work at runtime needs to occupy some resources, and this is, in our case, the memory. And then in plain native image, it's quite low. But then in the native image optimized, the memory went a little bit higher. Does anyone remember or maybe has any ideas why memory is higher in this second case? Sorry, louder? No, the XMX setting was the same, but what changed here in this case was that I added G1 GC, and I got better peak throughput, so we have better high performance, but it does come at the cost of having a bit more memory used by our application. But this is not a bad thing. I think this is an expected trade-off. So if you want to get something such as a higher performance, it is expected that you trade something off to get that high performance. And in our case, it is the memory usage. So G1 is known to be using a little bit more memory. This native image config out of the box, it always uses serial GC. So for peak performance, most cases G1 will be more winning, but it does use a little bit more memory. So this is also a trade-off you get to make with native image. You can have higher peak performance, but then you would need to use G1 GC. But still, I would say it remains reasonable and still lower than the one with the JVM. OK, so this was our benchmark. How am I doing on time? All good. My suggestion would be to make a break in half an hour, so we can have one break and just have 2 parts of the deep dive. All good? Good. Now, let's talk about more memory and performance optimizations. And I have a few more tricks to show you, or maybe not tricks, but like tools that we have in native image. So we have discussed these basic performance optimizations, or some that I think will be more useful to the wide range of users. But I also have for you a more advanced performance tooling that we will also explore here with you. So the very first thing, I want to show you a flame graph of, again, the same Petclinic application and how it uses the CPU. Because first of all, I'm a big fan of flame graphs in general as a concept. Any more flame graphs fans in the room? Okay, quite a few people, very cool. So there are basically two ways how you can build flame graphs with native image. One is, let's say, if you're running on Linux, you can just use plain Linux tooling such as perf, collect data, and then visualize it as a flame graph. But what's even easier is if you are using our build reports, as a part of that build report, we will produce a flame graph of the CPU usage for you. So let's just give this one the time to load, because honestly, that flame graph there is massive. So the whole report is taking a bit to load. For those build reports, again, this is something that have been heavily updated in 25. So I will talk more about them in the second half. But the part that is interesting for me right now, as we talk about performance, is this sampler output. And here we see this beautiful, massive flame graph. So this was our Spring Petclinic that was built with PGO. So this is with PGO, and we were doing sampling as our instrumented application has been running. This is also something you can do at home if you want to drill down into your application and see where it spends time, in which methods, and more importantly, where it spends a lot of CPU. So this is something you can analyze here with this flame graph. The way to read this, and it also has a little legend to make this readable for you, is that the red items are hot compilation units. So again, during this sampling, native image analyze your application, and those hot ones are deemed to be hot compilation units, where we will spend a lot of compiler time. So the red bars are hot compilation units. And in general, bars, and the way to read this is that each bar represents a function call. And this is not really like chronological, so this is not a timeline, but rather the longer the bar, the more often it appears in our samples. So the more often we think that method has been executed as we ran this instrumented run. And the red ones are hot compilation units, so where we will guide the compiler to spend a lot of time, because those we think are often executed, and it makes sense to optimize those if you want to speed up your overall application. Then the blue ones are methods inlined into those hot compilation units, and then the gray ones are called methods. So the methods that at the time of the observation were not called, so we will not be spending much time on this. And the overall sort of this kind of visual hierarchy here is the call stack. So the method here on top are the ones where our application ends up calling some particular method. And this is also interactive, so you can do a search here. So if we have maybe some, I don't know, random handler here, it will appear on the flame graph. So here I think we have some template handler, something from TimeLeaf. So if you want to really drill down into your application and see where it spends time and CPU, this report can be something useful for you. Let's see. Now, I'm wondering if I want to talk about the next one. So how are we feeling about the performance topic? Do you want to see some more tooling, or do you want to proceed to testing and deployment? So who wants to see more performance tools? OK, this is honestly not a very common result. OK, let's do more performance things. So we had talked about flame graphs. Those you can build with our build reports and analyze and drill down into your application. One more interesting thing in native image is that I told you that the way PGO works is you run your application as instrumented, you hit it with a workload, and as you do, we will generate and produce a file that gives us information on the profile of your application. So what is more often executed in your app? In my example here, let me see if I have the file. Yes. So when you shut down your instrumented application, you get this default iprof file, and that is the profile information of your application. But also, we can use the LCOV tooling, so the tooling that is normally used for code coverage visualization, to visualize that information that we see in that profile. So let's say you want to make more sense out of your profile. Let me see if I can make it happen. This is all sort of new and experimental, but I think we can look down into it. So you can just use alcove tooling of your choice. I will use this one, but I think you can even use some standard things like Gen, HTML, etc. And I have built my application with those specific flags for profiling, but using alcove tooling. So this will all become clearer in a second when we look at the actual app. So this is my Petclinic. I dropped it here, and this is my whole application as was seen during the instrumented run. But just stay with me. So this is not information on the code coverage, but rather we use the existing code coverage infrastructure and tools to visualize what we see in the profiling run of your application. So let's again retrieve some random handler methods. I don't really like that one. Let's give me something with a bit more info in it. OK, I don't mind this class. So for this class, the info on top says that this is, where are you? So this is line coverage. Normally, it would show you info on your code coverage in your application. But in my case, this is visualizing information in my profile. So this tells me that for this specific, let's say, handler base Java class, 100% methods of that class appeared in my profile. So again, we will spend more time here optimizing that specific class and its method because we saw more of it at the instrumentation run. So this is a way to visualize what's in your profile because that profile file is quite heavy. For my Petclinic, it's maybe, I don't know, 40 megs. But this tooling just gives you in percentages occurrences in the profile parts of that specific class per methods. So for this mapper.java, 77.8 of methods of that class appeared in the profile. So this is, again, a rather warm part of the application where we will spend more time optimizing that application. So this looks, I would say, a little bit extreme. Again, for Petclinic, it's a larger application. It's a very big file. But this, again, can give you more view into your application, the way native image sees it, and which part of native image of this application we will optimize because we saw more of it being executed in this training run. And the last thing I want to show you here in this space will be one more thing since we are in the Linux space. So I can do this. Let's go to our Spring Petclinic. And here, I think I can just do perf stat and pass my application target. Let's do Spring Petclinic, and maybe let's pick up the optimized one. And then I run it, and let's imagine it runs for a little bit. I don't need to go click it around, but let's say it ran and it executed some work. So now when we kill it, we also can just use plain Linux tooling to analyze our application. So in this case, 0.02 of CPU was used, which is similar to the time command that we did in the beginning, but here it's a bit more detailed. Some other instructions, some other interesting info that I can see here is we have almost 2 instructions per CPU cycle. I think it's a very good number. It means our application is quite efficient. And then we don't have any branch misses at all in our application. So again, because of native image and how we compile the application, there is way less dynamism at the runtime. So there is no burned CPU cycles on some operations that were speculative but never happened. So with native image, the runtime performance of the application is very stable and very predictable. This is also something you might have seen when I was running my benchmark, where our application had the same performance at warm-up and the benchmarking round, so it doesn't need to warm up. It's very stable over the time. Now I think we are actually done with the performance section. This is everything that I wanted to tell you around performance. The TLDR of this part will be that native image is often sort of known and used for startup performance, for memory usage, packaging size. But if you can spend additional time and optimize your application for peak throughput, if you really need it, you can also get a very high peak throughput at runtime. If you are not willing to do any manual PGO, etc. optimizations, at least I would recommend that you use the -03 flag. And specifically also in Oracle GraalVM, it will give you additional ML inference for your profiles in addition to more compiler optimizations. Now, this was all for the performance part, and I will be happy to answer any more questions that you might have after the session. Let's briefly talk about testing and deployment, and then we will have a break. So for testing, our general approach to native image when it comes to testing and developing, debugging your applications, etc., usually we recommend that you develop your application on the JVM, and then you treat native image as a more or less deployment step closer to your deployment. And you don't need to compile the native image every, 5 minutes as you introduce your business logic changes, etc. This is just not productive, and honestly, it's not worth it. So we do recommend that you keep building and testing on the JVM and compile the native image, maybe in your CI/CD, or maybe once a day, or maybe when you introduce new dependencies and you want to make sure that everything still works. But other than that, you can just rely on your framework support and on your tooling support to not having to recompile your application all the time. But if you do want to test native image applications specifically, we have a bunch of things available to you. So first of all, you can just run your test in the native image world. It's quite interesting to see it when you see it for the first time, because you run your, let's say, native test maven command, and it compiles your tests themselves as a native executable, which makes sense because they need to be running correctly in the native image world, but still it's quite interesting to see. And then we have some nice support from various libraries and frameworks and tools. So for example, from JUnit, you can have those two specific annotations to either enable some tests in the native image world. So maybe you want to have some tests that only test native image behavior. Or on contrary, if you know that you will not be testing something in native image, you can just tag those to disable specific tests in native image world. So again, you can have more flexibility there. And there I also want to mention to look at your framework modules that are available to you for testing. And I want to give a specific shout out to Micronaut Test Resources and Quarkus Dev Services for their integration testing support. That works really great with native image, and then you can test your application and the way they work with your databases and any other dependencies you might have. Now, I want to talk now about deployment options. And for that, the first thing we need to discuss is the packaging and linking options in native image. For that, we will switch to a different demo, and we will look at our native Spring Boot application, which is my sort of reference application for all things GraalVM and native image. So the first thing to know about native image is I talked a bit about how native image builds a native executable that can run as is without the JVM. So as far as your application code goes, your JVM, your dependencies, that native executable will be fully self-contained and fully functional as is. But still, even as a native program, you do depend on some libraries, dependencies provided by your operating system layer. And this is where all those different linking options come into play. So the first variant of building native image applications here is fully dynamic. And I think this is something most of our users use. And that is when you build your native application, but then some of those libraries from the operating system layer, being that your Linux, Mac, or your container-based layer. So some of those will then have to be provided by that underlying layer that executes your native image. So if you have ever built a native image and you did not add any specific flags around linking, you were building this fully dynamically linked application, which means that once you need to deploy your application, those are provided by the operating system layer, and I quite like this approach because this means that if I need to patch up my application, deploy a new version, I only recompile my application code and I deploy it. And then let's say if one of those libraries provided by the underlying layer need to be also patched and updated, this can be done separately. So either I can update them separately, or if I'm working at a company and we have some sort of infrastructure team and they provide for me this deployment platform, so they can take care of those dependencies and making sure I'm using always the latest version. But basically, those two things are decoupled. So my application depends on those base libraries, but they are decoupled in a way how the application is built. And then on the opposite side of the spectrum, we have fully static applications where I can bundle and compile everything together among my application, but also all those libraries that need to be provided by the underlying layer. And here in this mode, my application is truly fully static and fully self-contained because it doesn't need anything to be coming from this underlying layer. It has everything that it needs inside. And many people like this mode because this gives them the most control and the most compatibility across all the different kinds of deployments. You would never have an issue that some version of, let's say, glibc is incompatible with the application that you have built, etc. But so this is sort of more predictable, more controllable, but also it means that every time you need to introduce application changes, you need to recompile the whole thing. And also, if you want to patch up any of those libraries, you also need to recompile the whole thing. And but in general, this is also quite useful and used by other community members. I just feel like most users actually use fully dynamic more often, but static does have its own use cases. Does anyone in the room build fully static images? Okay, 2, 1.5 arms, I would say. Okay. And then there is a middle ground, which is called mostly static, where you can have sort of a middle ground, and you can compile some of those libraries inside, but then glibc will still need to be provided by your underlying layer. So the TLDR is, if you do not have any specific requirements, I would suggest that you build fully dynamic, but then fully static gives you a way to deploy your application in a very small from-scratch container because it is truly self-contained. So you can just choose what works best for you. And also talking about this, let's look at some of the deployment options that we can have for native image. So let's go to our native Spring Boot. And this is the project that we are looking at, where I have built a bunch of container images with various kinds of linking, and then going from JDK to native image, and trying to reach that like smallest possible building and deployment strategy that I can recommend to you. So let's see what we have built here, Docker images, and we will grab for our specific native Spring Boot application. Native Spring should be enough. And here we went, or I went, trying to optimize my container image size, going from full JDK to going to the smallest image size. But this is a native Spring Boot application. It is Spring Boot. So in this case, I could not have used the from scratch container because Spring Boot being like having a web server and everything, it does need some extra things from the underlying layer around certificates, time zones, etc. But I think we still reached a reasonable result. So going from the JDK, I know this is not a good strategy. Everyone tells you not to do it. But just having as a baseline our full JDK along with our application, we have a container size of 480 megs. And then we can do distroless, we can do JLink, we can shave off progressively the size of our container image. But then if we want to really optimize for it, in the end, we can arrive at the Spring Boot application where the full container image size is 58.5 megs. And this contains my full Spring Boot application along with the container that is needed to execute it. So let's look at how we arrived there and what is that final application. So this was my Docker build to build that specific application. And what we are getting here is we are getting our GraalVM native image, latest 25. Then we are compiling. And as we are compiling, we are picking up two profiles. So we are compiling inside Docker. And there we are picking up our native profile and a static size profile that I have created specifically for this application to optimize for size. So let's see what's in that static size profile. Let me just find it. Size, but I want the other one, this one. So the arguments that we have built here are quite a few. We are building with static, and then we are statically linking in muscle libc. And then when it comes to the image size specifically, we have two flags here. So one is -os, that is the one that we have seen before, and that optimizes for size. And this is something very new and very cool in GraalVM.25 that we have just added, but you can already give it a try. And this is, and you can, as you can deduct from the flag name, is also using ML, but this time we are not using ML for peak throughput, but rather we are using it for the image size. So we are using another ML model to optimize for the best image size, and again, predict which parts of the application can be further optimized for size. And this is the profile that we have picked up for our native application. So with that, we have built our smallest image size for our Spring Boot application. And let me look again at the file. This is the one. So we are then pulling this distroless image that will be our deployment image. It's quite small, but contains those few things that our native Spring Boot application needs to be fully functional. And then we are just picking up our compiled application, and that is our entry point. Let me see if I can actually run this and see that it's still doing OK. Let's expand this and let's clear up. All good. So this is our standard Spring Boot. You can see that it was quite fast, but this is now running from a container, so our output looks a bit different. And it started in 88 milliseconds, which I think is a good result for the basic Spring Boot app. So when it comes to deployment, those were a few things that I wanted to mention, and specifically when it comes to containerizing our applications. You can also scan those images that you have produced, including native image, if you want to detect vulnerabilities in your application. And then two more things that I want to mention here is one is Buildpacks. So you can also use native image with Buildpacks. We have our own Buildpack. And one more cool thing that I want to mention is GitHub Actions. I'm a big fan of GitHub Actions. I think GitHub should start, I don't know, paying me at some point or giving me credits, because I always talk about it. But basically, this is my native Spring Boot application, the same that we were looking at before. And I have it set up with GitHub workflows to be building every time on push. And I'm building for using GraalVM GitHub Action. We have our own that you can use. And here, in this case, we are building a native application of Spring Boot, and then we are uploading our artifacts. And I think this is quite cool, because then if I go to my GitHub Actions, I can see that for my, let's say, update to 25, our jobs have been finished. They are all successful. And as the result, we see our macOS artifact generated and Ubuntu artifact generated. And I think this might be one of the good ways to approach that cross-platform compilation with native image, because, as I said, we cannot out of the box compile for different platforms. We are depending on some specific JDK classes. But with something like GitHub Actions, you can build artifacts for whatever platform that you need. I know that some open source projects already heavily use this, such as, for example, JReleaser. And you can set it up in a way that you can build for all your target platforms and receive your artifacts on those platforms. OK, this was that for deployment. And I think now we can make a short break. Let me just check on time. So let's do a 10-ish minute break and meet back here at 3:05, OK? See you in a bit. OK. Welcome to the second part of this deep dive. We just have one more generic topic to cover, that is monitoring and observability, and then we will dive into GraalVM.25. And you will be the first people ever outside of our team to see one new big major project of GraalVM being demoed live. This will be super cool. I'm very excited about it. So let's go. So first, on the generic note of monitoring, I would imagine many of you, if you're deploying your native image applications to production, you want to be able to monitor and trace them and debug any issues that are happening around in production. And you might be wondering what are the tools and libraries and frameworks that you can use for that. So when it comes to observability and tracing, the number one thing I can recommend is Micrometer. Anyone in the room using it already? Quite a few people. I'm very happy. So it's a very nice sort of universal vendor neutral framework for collecting metrics and traces and logs of your application and exposing it to a wide range of backends. Somehow in my head, it's like more tightly connected to Spring Boot, but it exists also for all the other frameworks out there. For example, Micronaut has a very nice Micrometer integration where you can look at different things, expose different endpoints, collect metrics, etc. So this is the number one thing that I would recommend that you use for your native image applications, and has very nice built-in support for native image. And I would like to see if we can see some of that in action. In the meantime, during the breaks, I started my observability stack, which is quite massive. Every time I do this demo, I pray that it works. It never failed me, but still it looks rather scary. And then we will run two applications. One is a server application, so that one is now starting. And then we want to have a bit more advanced sort of system. So we will also run one more client application. And as you can see from my command line, those are native executables, right? They are green, so those are native programs. Those are already compiled and running as native executables. And this system is built on Spring Boot using Micrometer, and it collects and exposes a wide range of things to our Grafana backend. And the system is set up in a way where we have our client application talking to our server application, asking for info on specific users, retrieving that info. And this way we have like a little self-contained system that we can observe. And it's kind of nice to see them already interacting in those two processes, but let's go ahead and see. It might need another minute or half a minute to get actually info arriving to our dashboards. Let me close everything else. And let's see. OK, this was good timing. So it takes a while to propagate because there is Prometheus involved, and it needs to properly propagate all the data. But I think this is starting already to look good. OK, getting username for user ID something. I think that looks good to me. We can click and explore more info, and here we can see that our system is being visualized here across all those different operations. So we see the same thing that we saw in our program running, where we see that our client application sends a GET request to the server, then retrieves some random user info. And this is the place where we can explore all of that. And in addition, here we can also dive into logs for that particular span and get a better understanding of our system. And again, it already runs on native image. We can analyze even more things here. So we can go into the service graph, and here we see our little system of two nodes visualized in this nice way. Let me just switch it to a different layout. And here we can see more things, such as, for example, we can get our request rate for the system. So how many requests our server gets from the client. And on average, we arrive at like 2.53 requests per second, which more or less corresponds to what we see here. So this is, I think, one nice way to visualize and sort of gain visibility into the system that you have built with GraalVM native image, but there is more. From my understanding, talking to users, many are monitoring primarily sort of Kubernetes deployments, and then there is tooling that you can use out there. But also, I want to talk about specific tooling available in native image that you can use from the Java ecosystem. So how does all that tooling from Java correspond and work with native image? So one thing that I can recommend, and I think maybe it deserves a little bit more attention than it has right now, is VisualVM. So you can enable the jvmstat protocol in native image that is specifically intended for VisualVM by passing a flag enable monitoring equals jvmstat, this one. And then in VisualVM, you can observe things like threads, memory usage, GCs, the contents of your heap, etc. If you are deploying maybe plain native images, not in containers, I think that could be a useful tool for you. And then things like JFR, JMX, JCMD, we also have a nice support in native image. Some parts of them are experimental, but coming along nicely. And some of those are also very nice contributions from our community. So namely for GFR, JMX, the Red Hat team have contributed quite a bit of support and made it available to all native image users. And one last but important thing here is cloud vendor solutions. So many cloud vendors that are targeting Java developers see this increasing interest in native image, and they add support for tracing and observability from the platform, specifically for native image applications. So as an example, I often see people from Microsoft talking about Azure and the specific features they have around OpenTelemetry and native image to monitor their deployments on Azure. So whatever is your deployment scenario, provider, etc., you can check it out, and many of them offer some sort of tooling for native image. So that was the last big part when it comes to like working with GraalVM in production and in practice. And here I would like to switch specifically to 25. So 25 was released in September on the same date as your Java 25 was released. And this release is packed with features. So I'm really happy to talk about some of them. One is this thing that I briefly mentioned in the first half. So this brand new mode of building native image applications. And this is called Edge Preserve, but maybe the easier way to remember what it does was by knowing what was the first name of this flag. And our first working version of a name was called Edge Include. So this mode and this flag includes either your complete project into native image or specific parts of it. So I talked a lot in the beginning about how native image has this very cool, sophisticated analysis to understand what needs to be in your application and put everything that you need into that native executable, but also eliminate the things that you don't need. So we are very careful about being, efficient and stripping away everything that you don't need. But what if we didn't do it? Because sometimes users come to us and say, hey, I have this big old application. I know it will not work with native image. My dependencies are very old, or maybe they're internal. But I just want to compile everything there is. Like, I don't care much about the image size. Can I do it? And for the longest time, we were saying that this is not how native image operates. But then we thought, this might not be the worst idea. And I've introduced this new mode where you can instruct either to include everything completely from your project with Edge Preserve, and this will bundle and include everything. So your user code, your dependencies, the JDK, etc., into your native executable. Or what we rather recommend is that you go with a more fine-grained approach, where you instruct native image to specifically pull everything from one package or one module, or any combination of those to instruct native image that maybe you have one problematic library and you want to pull that library completely into your native image. And we think that this will be a big win for migrating more applications to native image, because with this approach, you will be able to just easily, with zero config, compile your application fully as is, or just by including those specific potentially challenging parts of your application into a native image. So this will be a very easy migration path. And I guess if I give you a minute or two to look at this and think about it, you will arrive at a similar question that I had when I first saw this. And the question was, but what about the implication of this, right? So what is the outcome in terms of packaging size, startup, performance, etc.? Let's talk about that. And here we have some measurements from the engineer from our team working on this, Wang, where he has built a Hello World application with Preserve All, but without the JDK. And where he arrived at was that Hello World ended up being 283 megs, and the startup time was quite reasonable of 34 milliseconds, almost 35. So to answer the question about the outcome for the characteristics of your application, the main outcome will be the packaging size. So I think this is quite expected, that if you pull more things into your project, or if you want to pull your complete project, you will have a bigger native image. This is expected. Now, when it comes to startup times and memory usage, those will increase proportionally as you add more things, but those will not be too bad. And the best part is that the peak throughput still stays quite good. It drops a little bit because maybe we are pulling in things that you don't necessarily need, but you instruct us to do so. So peak throughput might be maybe 10% lower if you're doing PGO, but overall you get a very easy migration path and then performance characteristics of the application still stay reasonable. We do recommend, though, that if you go with this approach, that you pull in specific packages or modules rather than the whole thing. But if you want to build your whole project as a native image, there is nothing stopping you now. And this is merged and now available in GraalVM.25. You can already give it a try. And even before the release came out, I already mentioned this to a few users at conferences who approached me asking specifically about like all the projects and the easy way to kind of migrate them to GraalVM. And I told them about this mode, that this is coming up in 25, and they were already very excited to give it a try. So I think this will benefit many applications. And here we looked briefly at Hello World. So as we said, the application is a bit bigger. I think it's expected, but then the execution time is not too bad. And I did some measurements of my own to show you how it looks for me. And let's see also this flag in action. So I think this was a Micronaut application. Let's see, target. Yes, so this one, Demo Preserve, this was a Micronaut also web application, sort of a reference implementation of a Micronaut app that I'm using for my demos, where I have a couple of classes, things for working with reflection, configuration, etc. So this is my application, couple of controllers, that reflection config that we looked at in the first part, and this is my POM XML, and this is my preserve flag. So here I'm using the preserve flag, but I am following that approach where maybe I don't need necessarily to pull in everything. So I'm not doing all, but I'm doing all unnamed. So this excludes the JDK and the items that could have been on the module path. But it does pull in all my user classes, and it does pull in everything from my dependencies. And I do have a few things there. So I have my HTTP client, I have my web, netty, validation, etc. dependencies. So the project, I would say, is not a hello world, right? It's still a framework application, but compiled with demo with hpreserve, it's 157 megs. So my whole class path and my dependencies and my user code ended up in this file, which is not too large. And then when we run this, target demo preserve, starts, I would say, very good in 30 milliseconds, and it should give us a normal response at the hello endpoint. I think we need to remap the ports again. So this is running on 8080. 8080 again. And let's close it and let's go again. Localhost hello. OK, I think this might be something about the connection to the cloud instance, but let's just do this. Let's do curl and let's do the endpoint. And it is running. It just does not propagate to my browser, but the application is up. So that was one of the updates in my 25 favorite features, and let's talk about more. So the next update in 25 is connected to this mode, hpreserve, and when I saw this, I was actually pretty excited because this might be sort of on the surface, but I think it's a brilliant way to extend this feature. So imagine you build your application with hpreserve, and you include everything from your project into that native image. So your migration was very easy. You arrived at that final executable, all good. But it is maybe a bit big. And also we can agree that this is not overly efficient because you pulled everything whether you need it or not. So the way we took this mode of operation one step further, we have introduced a brand new tracing agent in native image. Then in this case runs on native image specifically. So this is no longer on the JVM as we were talking when we were talking about configuring libraries. So this runs on that preserve all image, and it looks at what your application does. So similar to PGO, you need to start your application and hit it with a relevant workload, so that we can see what your application is supposed to be doing. And then when you shut it down, we produce configuration for you of everything that happened in your application. And we produce this precise configuration for native image around reflections, serialization, proxies, etc. So you can go ahead and build your application second time with that precise configuration in place. And then you can have a much smaller image, comparable to your normal native image because now you have configuration. So this is a two-step process where you can figure out configuration for a project that initially maybe was not compatible with native image. So two things to take away from here. If you want, you can build your application with hpreserve and just deploy it and run as is. Or if you want to improve its efficiency, slim it down, and also get maybe a bit of better performance out of it, you can do this extra step where you then run it with trace metadata and output the file, and you recompile the second time, and then you have this precise config to build a smaller version of your application. I quite like this. I think this is actually makes a lot of sense, and it's very useful that you can build the whole application and then strip it down because we can observe what your application does and what is actually needed at runtime. Now, the next topic is something that where we made a major update in 25, and in general, I think it's a very interesting part of native image, and maybe a part where we don't talk about it often enough, and that is security. So we have some users that use native image specifically for the security benefits. They tell us that, yes, we know all of that, startup time, memory, packaging, that is all very good. But for them, the main benefit is that this added layer of security that native image adds on top of your normal applications. So where does it come from? Native image, as we mentioned, operates under closed world assumption by default, and that means that things like reflection, serialization need to be configured and specifically allowed by those configuration JSON files to happen. And you might see it as a bit of a limitation and like an extra step that you need to take, but in a way, it's just a different sort of design choice, and also makes your application more secure and gives you more awareness over what happens in your application. So a native image application, then you cannot perform a random reflection or serialization calls on it because this is just not allowed. So everything needs to be specifically allowed and put by you on that allow list, either by you or by those libraries and frameworks that you are using. On top of that, as we said, by default, we are removing everything that you don't use. So this way, we also reduce your attack surface because there are fewer things to attack in your application as there are fewer things in the final app. And lastly, it's a smaller one, but sometimes people can attack applications using JIT compilation. So the JIT compiler becomes this attack vector. And then in native image, it's not possible because there is no JIT compiler anymore at runtime. But also, we want to make sure that you can have even more secure applications, especially if you work maybe in some corporate environments and you have some corporate security team that has policies and guidelines and wants to scan your deployments. So for that, we have added quite a bit ago support for SBOM in native image, SBOM being software bill of material. And then in recent releases, we have significantly expanded it. So at the moment, you have a lot of options how you can build a native image application with that SBOM support. So those are all the various options, how you can enable it, and let's talk about them. So the general flag is enable SBOM, and then you can pick and choose each of those, or you can even choose a combination if you need to have several types of SBOM included. So by default, probably the most common option is to embed SBOM inside native image. And since 25, this is also the default mode. So whenever you build a native image, we will include SBOM there by default, so you can more easily scale, maintain, and see what's inside your dependencies. So by default, you will always include SBOM. If you want, you can specifically disable this, so instruct native image to not include it. But we did a lot of measurements, and this adds very little in terms of image size and almost nothing in terms of image build time. So we think it's a sensible default to have in place. The next option we have is export. So you can export your JSON file as you're building your native image application. And then as you're compiling your application, alongside your executable, you will also receive this SBOM file. One more option is class path. So class path means that we will put that application, that SBOM, and expose it as a class path resource of your application. And this is very useful to integrate with third-party tooling. We will see it in a second. And then the last option here, it's quite, I would say, advanced and mind-breaking one. It's called class-level SBOM. And what this does is that since we analyze your application as we build it, we have a very good understanding of what's inside your application, on a class level, but also within the class. So we analyze what you need in terms of class files, fields, methods. On that granular approach, we know exactly what needs to be in your native image application. And if you want, you can output SBOM that will be at this level of granularity. So it can be class level, and it can be a huge file telling you that from this dependency, you are using those specific classes and those specific parts of those classes. Now, this means that if there is a vulnerability found in your deployment, but you can analyze your SBOM that you are not using that specific part of that dependency, this means that for you, it's a false positive. So I understand the sentiment that it's probably always better to patch up all the dependencies, but you can have a very good understanding of what is in your native image in terms of SBOM if you're using the class level SBOM with this insane level of granularity. And with that, I would like to show you some of that in action. And for that, we will look at an application that I have built with SBOM support. So let's clear this and let's go to our native Spring Boot. OK, and here I have built several versions of that application. And the one that I'm interested in at the moment is this demo SBOM. So first of all, I can just start it, target demo SBOM. OK, it starts. And let's see if we can retrieve it. And that application has been built with Spring Actuator. So if I go at the right endpoint, the Spring knows that my application contains a native image SBOM in it. So this is this class pass SBOM integration that I mentioned in the beginning. And Spring knows without any configuration to expose this under this endpoint. So how this can be useful in practice? Let's say I'm working and there is some security team at our organization that wants to scan all my deployments and make sure that they are secure. Or maybe I myself want to be confident that my deployments are secure. I can point that team, or if I'm doing my self-scanning, I can point my scanner to this SBOM endpoint, and they can find what is exactly in my deployment every time I deploy a new version. And then they can see by each dependency, each version, whether or not my applications are safe or whether some changes are needed. And what I quite like here is we also added this not so long ago. We added this new functionality of depends on. So we help you analyze in your native image app which dependencies depend on which. And I know that there is nice tooling for this around IDEs and Maven, etc. But this is specific to native image. So what ended up in my final native image, I can see the dependencies and connections between them here. So for example, my Spring Web MVC is in turn pulling in things like Spring Core, Spring Context, Spring Beans, etc. And I think it all makes sense. So this is something you can have and scan and have available in your production deployments. But what if you want to scan something now? Let's try it out. So I have built this application with SBOM on the class path, but also embedded. And this means that I can also retrieve it like this, native image inspect. And I want to get the SBOM specifically, and I want to get it from that demo SBOM file. So I can run this as is, and it will show you that there is sort of the same JSON file available inside. But a quick side note, I don't know about you, but I'm a big fan of cool CLI tools. So if you have this random huge JSON output, you can also pull it into JQ, and it will give you this very nice and usable and human-readable JSON output. But in our case, we want to do vulnerability scanning. So what we will do instead, we will put it into our vulnerability scanner of choice, and that will be for me Gripe. It just needs to be one that supports Cyclone DX, because that's our vulnerability, our SBOM format. Let's do this. And of course, it will now need to download new vulnerability DB. Let's see how the Devox Wi-Fi will do. I think, oh, okay, it's downloaded, all good. So now it's scanning. It says that it gathered info on 38 packages in my application. That's indeed how many packages that I have. And we should see if our Wi-Fi permits, yes, that our application has been successfully scanned, our vulnerability database has been updated, and there are no vulnerabilities in our app. So we can have peace. But this would be nice to have maybe deployed somewhere at work, but for the demo purposes, wouldn't it be nice if we did find some vulnerability in our application, right? Let's see if we can do it. For that, I have a slightly different version of this application that is called, intriguingly, native Spring Boot vulnerable. And the way this application is different, it's quite similar to the first one. It's literally cloned repo, but I have made one meaningful change, and I have added a JSON dependency and intentionally a very old version so that I know it will trigger my vulnerability scanner. And this might be sort of expected and reasonable, but it's not enough to just add this dependency and expect it to pop up in our scanning, because native image is smart enough to understand that I added it, but I'm not using this dependency. So I need to actually actively use it in my app for it to be visible in the scanning. So for that, I modified one of my controllers, and I'm pulling in that dependency so that native image sees that it's actually used, and it bundles it into our native executable. So let's give this one a try. For that, we will navigate to that folder, native Spring Boot vulnerable. And we will again do the scanning. So native image inspect. And we need SBOM. And this folder has already precompiled the same version of the application, but now with that JSON in place. And this we can also put into Graal. So now it scanned very fast this time, and it does say that, yes, indeed, you have some vulnerabilities in your application, and they're actually quite high severity, so you need to go ahead and fix them. So we think those features should be quite useful for you if you want to deploy applications in production environments, but also if you have any feedback or if you have any ideas of other specific native image features, we are very open to hearing about it. Now, we talked about SBOM support, and we looked at the demo, and we scanned our native image applications. But then I want to talk about how we made one more step in 25 to make your applications even more secure and protected. So the way we see it, and as I mentioned, many of our users see it, native image already performs what we call basic obfuscation out of the box, because native image starts at your application code, it's bytecode, and it compiles it to a native executable. And along the way, it strips away things you don't need, it optimizes your code, performs compile optimizations, and in the end, you end up with a native code that is much harder to reverse engineer and go back to the source code. I'm not going to say that it's completely impossible to see what's inside the native image, but it's much harder because it does perform that basic obfuscation just by its own compilation strategy. But in this release in 25, we decided to take it one step further, and we have added something that we call advanced obfuscation. So this is the flag, h advanced obfuscation equals, and now also let's see it in action. It's also experimental option in this release. Typically, when we introduce new options, they are all experimental because we are looking for user feedback, but it's already looking quite interesting. So let's imagine this is our class that we want to make more secure, right? We have our secret class, and then we have some secret algorithm. Maybe we have some unique knowledge at our company. Maybe it's some trading algorithm or something. And it's very important for us that it stays private. It's our intellectual property, right? So let's run this as is, and it's intentionally throwing an exception so we can see the stack trace and see how our application would perform if such an exception happened, because it's live, exceptions do happen, right? So let's go there and let's run this application as is. So Java secret class, and we could just start from the source. So it looks perfectly normal. We received the same output that we expected. We have our class name, which would have been fully qualified class name, our source file name, and then our exception happens, and it tells us that exception happened, namely in the secret algorithm of the secret class. Granted, this is maybe an overly generalized implementation, but it gets the point across. So what we can do here is we can build this application with this advanced obfuscation flag, and I already did, and I have it compiled here as this little secret class. By the way, we can stop here for a second and appreciate how small the application is, because I normally work with and demo framework applications, but plain Java can compile down to like 6 meg app, and I can further improve it to maybe like 4 meg if I apply additional flags. So this is quite small. And when we run this guy compiled with advanced obfuscation, what we get instead is that our class names and method names, etc., were replaced with those generic identifiers like A, B, etc. So even when that exception happens, it's hard to retrieve what exactly went down and which methods were executed. And let's say if someone were to crash our application and obtain that stack trace, they cannot easily go back from here to our source code. So I think this can be quite useful. There are sort of limitations to how we do this. First of all, classes, there are things that we preserve completely that we don't obfuscate. So if this was, let's say, my Spring Boot application, I would see some of the Spring methods printed in the stack trace as R, but then my actual user code is obfuscated. But honestly, I don't mind because Spring is open source. It's not at least my intellectual property, so I don't mind even if someone obtains the stack trace that they see Spring Boot in there, as long as they don't see my private code. But let's say this crashed and you need to debug it. So let's say this crashes in production and you get this beautiful stack trace. How do you go back from here to your source code? I'm glad you asked. So what you can do is, and I recommend that you do this, you can build this file with this flag advanced obfuscation equals export mapping. So this is why we have the equals, because it can potentially take a value. And if you do this, you will receive this, obfuscation mapping JSON file that instructs you what has been obfuscated to what. So my application is not that big, that's why it's not a very long file. But basically, this gives you a way to debug it. And what's better, you don't even need to manually map things here. We thought about that. And we provide you with this deobfuscation command, where you can take this stack trace that I have received here, store it in a random file. The name doesn't matter. I just did error log. And then you can run this deobfuscation command. And then when you do it, let's close this and let's move higher up. You will receive your normal full Java stack trace. So there is a way to then debug it and properly work with such an application. So I think this is very cool and very interesting. And if you have any feedback for us or for our security team, we would be very open to hearing about it. Let me just go back to my agenda for today. README, this is the file. Okay, so we talked about some things in 25. We talked about security. We saw in action vulnerability scanning. We saw advanced obfuscation. And I want to mention some of the tooling that comes with native image that you can use as you develop your application. We already saw a little preview when we were looking at flame graphs in Spring Petclinic. But overall, this is a report that you can get from native image if you add one flag, and the flag is emit build report. And you can have this HTML report every time you build your application if you want, or maybe if you debug specific issues. And this is a nice report that you can either get as HTML as I have here or download as JSON. And this talks about your build, what we've seen during the build time, how many resources used, etc. But most importantly, you can compare those across times. So let's say you have your constant deployment of an application. And if you build a build report every time, you can see some changes there, such as, for example, if the image heap spikes, maybe there is something you are missing, or the code area spikes, or the analysis suddenly starts to look very different. This could be your sign to troubleshoot some things. And overall, the build report gives you info on what was the GraalVM version used. It shows you the little security report, says, that, for example, Cyclone DX SBOM was supported. And in this one, I did not enable obfuscation. So it tells me maybe I want to additionally protect my application and enable it. And then you can drill down into code area or image heap and see what is in your application and what makes it larger or smaller. And one more note here is that this is a breakdown of the overall image. So the structure of the image is that you have your code, you have your image heap, and then you have other data. So normally this section should not be too large, should not go above maybe like 10% of your image. So if this goes too big, this could be your sign that there are some extra files that you maybe do not necessarily need. An additional place to optimize your image size would be here for the resources. So this is Spring Petclinic, and even though it is a bigger application, I don't have any resources that look too out of place for me. It all looks fine. This is also another place where you can see your dependencies and retrieve your SBOM. We talked about Flame Graph before. And this is something quite cool that we have introduced in 25. So let's stop here for a second. In the beginning, we talked about using libraries and how in some cases you might need those configuration files to make the libraries work. But wouldn't it be nice if there was some tooling that would recommend to you what are the specific places that you need to watch out for? So we thought the same thing, and we have added this new report. It's experimental, which is indicated by this little experiment emoji there. And this shows you for each of your dependencies whether or not we see configuration files being provided for that particular dependency. And then when we don't see those config files, but we think they might be needed, we show you a little sign to look and investigate that dependency. Now, currently, we are being overly cautious, and we are tending to show more libraries needing investigation. So just to be careful and show you maybe to check more things rather than less. But this does not necessarily mean that this is a problem. This means that this just needs a double check from your side. So because there was some sort of dynamic access call, maybe a reflection, resources, etc., so maybe go ahead and check out that library. So if you really want to check your libraries, make sure that they work, but you don't want to check everyone manually, this report could be useful for you. And now it's experimental, but we plan to expand this in the future. Okay, let's see. Those were build reports and more about ML in GraalVM and in native image. So we have talked about how we have ML in native image to optimize your application's performance. And the way to trigger ML to infer profiles and to optimize for peak throughput is to pass this -03 flag. -03 means optimize for the best peak throughput, so max compile optimizations. And by this, we mean that you also imply that you want the best peak throughput you can get. So here in -03 in Oracle GraalVM, we will automatically trigger machine learning for profile inference to try and infer your application's behavior at runtime. So in this release, we have refined that model. We have even more performance with ML. We might be like 8% out of the box. And we plan to further expand it in the next release, maybe get it to 10% peak performance improvement over not having profiles in the first place. And what's new, you can now also trigger this ML profile inference in -02. So you can have a rather fast build, but not quite all compile optimizations, but still ML for peak throughput. So in general, O2 is a good trade-off between build time and peak throughput. And what is also new, we have added another kind of ML. We briefly talked about it when we talked about optimizing the size of container deployments, where you can use ML to produce smaller images. And there we will again try to infer what is possible to optimize and squeeze to give you smaller executables. Now, the next one is quite a fun one. I'm wondering how many of you are like actively using or building position-independent executables? Last time I was at a conference, it was also like 0 hands. So I'm glad it's not just me who had to do some digging when we introduced this feature in 25. So position-independent executables are executables such as your native executables, your normal native images, or shared libraries that can be executed correctly no matter where they are loaded in memory. And this is not a new groundbreaking concept. It's a more or less a standard practice, especially on newer platforms such as recent versions of Linux, etc. This is just something that happens out of the box without you being aware, because this enables additional security hardening features for your application, and namely this enables address space layout randomizations, meaning that it's harder to attack your application because it can be loaded anywhere in memory. And at least traditionally, maybe less so lately, those position-dependent executables were associated with a bit of an overhead in terms of startup time, memory usage, packaging size, because there was a bit more work for the operating system to do. once that application loads, and it needs to do all the relocation and all the other overhead operations. And the way to tackle this will be to use relative code pointers that is supposed to eliminate that potential little overhead of the position-independent executables. So this will not make your application, I don't know, 2-5 times faster, but this will make sure that you can use position-independent executables and have extra security with no performance penalty. And this is new in this release. I did some experimentals to try it out. I think this would need to be Spring Boot. And here I have my couple of versions of application compiled. So one is demo PIA, or some people call it Pi. Let's look at what's inside that application. And this is my POM.xml. So for position-independent executable, normally you don't need this, but I just did it because I wanted to make sure that I'm building a position-independent executable, because this heavily depends on your version of Linux, compiler, etc. So here I'm just passing a flag to specifically enable it, but honestly, normally you don't need to do this. And this will be our baseline, so a normal native image, but specifically compiled as a position-independent executable. And then I have one more version with relative code pointers. So this is introducing that additional new feature in 25 that is supposed to make those applications slightly faster, slimmer, and less memory hungry. Again, just to emphasize, this is not a huge difference, but it's just a good thing to have out of the box. So let's start our applications, and we will again time them. So user bin time verbose. And here goes my baseline position-independent executable, PIA. And it starts, and let's just give it a couple of seconds to run. And then when it runs, we can kill it. And I'm at the moment most interested in memory, and my max RSS for this normal position-independent executable was, let's say, 85 megs. So now if I again time one that has built with relative code pointers, what I get here, it starts, and I will also give this one a little bit of time to run and sort of do some work. And now when I kill this one, it's at 81 megs of RAM. So not a tremendous difference, but I think a nice little improvement to have if you're building position-independent executables. And the way to memorize what you can get from this is if you have been building position-independent executables in the past and you saw a bit of that memory, maybe startup time, maybe packaging overhead, that will be eliminated if you use this flag. Or if you were hesitant to use them, to build them, because you were thinking about that overhead, then just proceed with the flag and they will perform on the same level as normal native image, but with additional security sort of guarantees in place. Also in this release, we have extended support for the FFM and Vector API. I know that many users will be excited. This is available in both Oracle GraalVM and GraalVM Community Editions, so you can have fast operations with Vector API, and also for workloads where maybe you have some sort of Java implementation, maybe Java inference in pure Java, you can now run on native image on a wider range of platforms. For example, for my Apple Silicon Mac, I can just compile and run natively on it. If I'm using FFM, FFM is now a supported platform for native image. And there have been some other changes around native image. For example, we have simplified this reflection configuration. It is now one big file, reachability config JSON, and we did a lot of work to make it easier to work with and add additional developer tools for you there. And for that, I want to switch to another fun demo, and then we will talk about embedding languages. So you might know that GraalVM can help you embed languages in Java. You can extend it with things like Python, JavaScript, etc. And I want to show you one such demo. So let's go ahead there, and this would be Erlang demo. And actually, let's first start it and see if we can get it to run. Okay, this starts, and we can see that this is a native application because it started. It was executed as a native program, but also it started in just 200 milliseconds. And then when we go here, localhost departures, we will see my imaginary application for an imaginary airline, which might or might not look like a Swiss airline, like as you can see by inspired colors. And this emulates sort of a working app of an airline. And what is underneath here is a normal Spring Boot application. Let's go there and let's see what's inside. There are a couple of things. I want to expand it to add more features there. But for now, we have a couple of repositories and controllers to expose this sort of airline functionality. And more interestingly for me are the dependencies in this application. So I see my normal Spring Boot, time leave, data GDBC stuff, H2 we are using as our database, and here we get into the languages. So I'm using GraalVM Python, and I'm specifically embedding my Python. And yes, this all runs as native image. So you can run such an embedding application on Java, but also you can just compile the native image because why not? And there is no magic. Python will be still dynamically executed at runtime. We will bundle a little Python runtime, which is our GraalPy. So Python will be dynamically executed. And this is our application, and there is a bunch of other things that we can do here. For example, let's imagine that we are a boarding gate agent, and we need to generate somebody's boarding pass. So we can have that person's name and last name, and again, imaginary booking reservation. And this generates a boarding pass. What's cool here is that this QR code comes from Python. I'm sure it's something similar can be found in Java, but for me, I just wanted to, use Python for something fun. So here, this whole QR code generation functionality is coming from Python by using our GraalPy context and pulling in this package. And if you are ever wondering, I must say I was never wondering before I started working on this demo, you can scan the QR code and see that it's real. So if you're ever wondering what's encoded in your boarding passes QR code, it's your passenger name and last name and booking reservation, but also some metadata for the airline. And for us, this functionality here is coming from that Python package. And the way to pull this in is also, I think, something that was very well designed by our team. We did a bit of a revamp here a few releases ago. So if you have ever built such a Polyglot project, you know that the biggest challenge there is how do you bridge all those ecosystems together. Let's say here we have Java and we have Python, and it might be hard to configure, all the packages and build processes for both the systems. So the way we did it, I think, is quite nice, is that I can have one build file. In my case, it's Maven and POM.xml. And there I can specify which Python packages I want to use and which versions. And then as I package my application, GraalPy will bundle for me the whole thing together and make sure that I have the correct versions and it all works as expected. But for me, this is the best probably developer experience that I can have for Polyglot applications because I can just specify them from my normal Java build file. So this is where we used Python for the QR code, but we all know that another kind of thing where Python is widely used is everything around data visualization and data processing, NML, and all of that. So I thought we can also, for our imaginary airline, use some Python to do some data visualization. And for that, let's go to a different endpoint here. And here we are doing some sort of data visualization and statistics using, again, Python. So for example, we can see that for our airline, we fly most often to Charles de Gaulle, Heathrow, and Vienna. And we can also analyze our flights by statuses. So most are scheduled, there are some delayed, and there is one that is boarding at the moment. And I think this actually looks quite nice, and it was fairly easy to make happen with the Python embedding. So again, you can tell me how you feel about those things, but for me, this is a pretty reasonable sort of Spring Boot code with a little bit of GraalPy in it. And then the actual charts are coming from Pygel. There's a rather kind of popular Python library for those sort of charts. And the syntax is, again, fairly simple here, and you just code straight in Python what you want to see on that chart. So we have one for our destinations, and then we have one for our flight statuses. So this is quite cool, and this is one of the ways how you can embed Python in your Java applications. Let's see. This was the embedding Python one. OK. And those were at least the key features of GraalVM.25 that I wanted to mention to you. And now I want to switch into sort of like future work and talk a little bit with you about what we will be working on moving forward. The first thing is native image layers. So this is a big project in our ecosystem that we are working on. We have been working on for a while. We have some good results, but there is still work to be done. And this will be another sort of groundbreaking way of building native image applications. So I talked a lot about how native image bundles everything that you need in your application, and then it's fully self-contained, and you can deploy it as is, and it will run completely functional and self-contained at the runtime. But also, what if we rethought that concept, and what if we introduced the layering approach, sort of similar to Docker layers, where let's say if I'm using Micronode, I can have my JDK base compiled, I can have my Micronode dependencies compiled, and then every time I want to recompile my application, I introduce my application changes. I only recompile the top layer that I actually wrote, and the base layers stay compiled, and I'm just linking to them. And this way, we think we can achieve two interesting benefits for native image. One will be that your build times will be much faster because you are only recompiling that thing layer on top of those dependencies. You don't need to recompile the whole JDK and dependencies every time. And what's even more interesting, once you deploy your applications, let's say you deploy applications to the cloud, you can have, maybe you want to have your 5 instances of your application for load balancing, and then you can deploy such an application, have all your base layers deployed already, and share them between those application instances, and even further reduce the resources usage of your application. So we think this will be quite interesting. We already have some good results where we can compile framework applications using layers, and we have more work coming up in the future, so stay tuned. The next update there will be also quite interesting. So this is very, very recent one. This was announced maybe like a week ago. Quite often users ask us to add more GC options to native image, and while there are already quite a few, and we also keep fine-tuning and updating the existing ones, sometimes they ask us for brand new GCs in native image. And if you by any chance have been at our BOF here at DevOps last year, there was a question from the room, what about adding something like Shenandoah to native image? And now it is happening. So here you can see that this ticket has been created by people from Amazon, and they will contribute Shenandoah to native image. This work has already been announced. So they will do the bulk of that work, and then also our team will contribute infrastructure that is needed to add more GCs to native image. So this will be a collaboration project, but that has been started by Amazon. And we think this will be quite interesting. Probably this will also take a bit of time to arrive, but it seems to me that for native image applications, if you want to run with larger heaps, or maybe if you have specific requirements around latency times, Shenandoah could be an interesting case for you. So we are looking forward to this collaboration. You can also let me know if you are interested in using Shenandoah for your applications and what specific use cases you think would be the most kind of important for Shenandoah to meet. And in general, if you want to see what we are working on, all the things that I'm showing here is in our GraalVM community roadmap on GitHub. So we're trying to be a good open source citizen and share with you the work that we are doing and what is coming up. Here are a few things that we have delivered in 25, and there are quite a few things that are planned for future releases, but we are already working on some of those. Some of those are already in progress. So that was Shenandoah in native image, and I want to show you one more interesting thing. So native image is something, as we discussed, that takes your Java bytecode as input and outputs a native executable, or it can be also a shared library. But technically, there is no limit to what native image can output for your application. The limit is only your imagination and the implementation details. So technically, native image can output something else, such as, for example, WebAssembly. And this is early days. This is still ongoing work, but I would like to show you a little bit of preview of that work. So we have here this little page that is hosted on our GitHub. And if you look at this, this might look to you as of some, I don't know, Java learning environment, playground. And you might think that maybe this is coded in something like, I don't know, just plain HTML and CSS and JS to show you how potentially Java can be executed, but it's better than that. So this is Java C on WebAssembly, the Java C compiler from Java. that has been compiled to WebAssembly by native image and deployed to our GitHub repo at this endpoint. And to show you that it's live, we can compile this little class that we have here that says hello WebAssembly. But better yet, so you don't have to take my word for it, we can take and expand this class. So this is all fully functional. And then we can say something else. I don't know, we can do hello from Devox maybe. We can compile this one. Again, success in 26 milliseconds. And then we can disassemble that one. And we can see instruction by instruction what happened inside. So we see that our field has been loaded. We see our normal string hello from WebAssembly, invoke virtual. And then we see our new string that has been added hello from Devox. So this is a little bit mind-bending, but this is indeed Java C that has been deployed on WebAssembly running purely in the browser compiled with native image. And the name of this project is WebImage. It's early days of it, but as you can see, it enables some very cool use cases. And if you want to learn more, you can talk to me afterwards, but also there is a session from a colleague of mine, Fabio Nibhaus, later this week, where he talks about more of this in detail. And now I would like to get to the last demo that I wanted to show you, and that is a demo for Project Crema. So Project Crema, I'm wondering how many of you have heard about it already? Okay, my manager have heard about it. That's reassuring. OK. So Project Crema, as you can see here again in our roadmap item, will be a way to open the world for native image. And I cannot even choose the words to describe my excitement about this, because this is extremely cool for native image. So we talked a lot about how native image compiles the application ahead of time. The runtime hasn't happened yet. So technically, we have no way of knowing what will happen at runtime. And we have some tools and techniques to get a glimpse of what will happen at runtime, such as PGO can tell us how your application will behave at runtime. But overall, the sort of core foundational principle of native image is this closed world. Because at build time, we need to know everything that needs to go into your application so we can compile it ahead of time. But then Project Crema is here to expand the definition of native image and expand what is possible with native image. And as the name says, it's an open world for native image. So it means we no longer operate under a closed world, and we can execute new classes at runtime. So if you have ever thought about it or asked us about it, you know that for the longest time, many people were asking us, but what about, if my library generates some bytecode on the go, or if something happens, I need to load a new class. And for the longest time, this was impossible because native image closed world assumption, and you need to configure all of that at build time. And we announced this project maybe a few months ago, but we've been working on it for a while. It's still early days. We still have a lot of work to do, but some of that work is already done and has been merged into our main line of development. And the way this works, it builds on the existing other projects in native image. So with GraalVM, always it all comes together. We compile our own compiler with native image. And with Crema, we are building on some of the work that we did for native image layers. And also, we are using our GDWP debugger from Espresso to open that application layer. So the way this works is that you have your base application layer that is compiled as native image, and then your base layer, and then we add on top a Java interpreter that can execute classes dynamically at runtime. So you're still running on native image, but suddenly it is possible for you to execute new code that was not visible, that was not predicted, that was not in any way configured when you were building your application. And for that, I would like to show you a little bit of demo. And I'm actually super excited about this one. No one has ever seen it yet at a conference. No one has ever seen it outside of our team. So this will be super new and highly experimental and just merged. So please cut me some slack if it doesn't work out. But I hope that it does. Let's see. So we need to go to Crema demos, and I want specifically this one. And here I have a bunch of files, and this is actually my Crema. So this is not Crema per se, because Crema is a way of building applications, but rather it's a specific application that has been built using Crema. And specifically, the way it came to be, this was the build script. Let me scroll down because it's quite large. So we see our normal native image command. Then we are unlocking some experimental options. We are preserving some classes that are needed for our Crema demos right now for demo purposes. Then we are passing the Crema flag. We are passing Java home. And the actual file that we are compiling is this one, source launcher. So source launcher is your normal file from OpenJDK. Let me see if I can quickly retrieve it by going to OpenJDK. OK, and here I want source launcher, and not the test, the actual one. So this is the file that is responsible for your JDK's capability of running Java classes as is, right? So compiling and running on the go, as I did in some of my previous demos before. So this is what we have built with Crema. And here I also have a bunch of classes that hopefully we will be able to execute. So let's see. First of all, what we will do, we will just run a hello world as you normally do. And this hello Crema is your normal Java program where we are printing a line. And then we are retrieving the Java VM property name. Let's see. Let's see if I can manage. So right now, the DX is not quite there. We did the work, but for the DX, I still need to do this. I hope and I think we will be able to improve this in the future. But for now, I need to pass an extra flag to execute things. And now that I have this in place, I can run my hello Crema. And it runs. It might not look like an impressive demo, but it's a huge deal for me, because this runs on native image. We saw that our application is a native executable, compiled as a native image. As we are retrieving the Java VM name, we see substrate VM, and substrate VM is the little VM that we embed into native image. So this is running on native image, executing a random file that I have provided at runtime. To illustrate this point even further, let's take some other file. We have a few things here we can look at. We can do this like .java. And we have a cool visualization. So we still run on the same native image, but their file, as you can tell, was provided by me right now. We can do some other fun and visual and crazy things here. We can run this random but pretty cool rainbow. And one more thing that I want to show you here is something called Grab It. My manager would not like the name, but I like the name. I don't know if you guys can identify this guy. So this is the GraalVM rabbit. And obviously, we can run it on Crema as is. So we just ran it, right? But we can also go ahead and modify it and do something else there. So this is our grab it. And let's say we want to add one more block there that also prints something. Print, and let's do hello, hello from Crema. And we save this, and we run again. And now we get, again, grab it, but now we have our new message. So my point being that it's possible with Crema to dynamically load and execute classes at runtime. It's early days, but I think this will be very interesting. I think you can think of many applications that would need to load classes randomly at runtime. And this bridges this gap between the worlds of dynamic code execution that you normally have on the JVM and the power of static ahead-of-time compilations that you have with native image. So the file is still quite small. It actually runs quite fast, but you can now load dynamic files at runtime, and then for libraries that execute and load and generate bytecode and runtime, it will be also possible to run them on native image with Crema. So this is something that makes me very, very excited. If you want to see more news about Crema, you can follow our news on GitHub. And this is something where we see a lot of excitement in the community, and we think this will be a huge step moving forward for native image and GraalVM as a whole. With that, I would like to wrap up. I want to show you a few final things. Where's our GraalVM in practice? OK, this one. So if you want to get started with any of this, I will share with you in a second a QR code with a repo on GitHub with all the links, demos, notes, also with the links to all those roadmaps items, so you can keep them and check them and follow the updates there. To get GraalVM, do our favorite thing, which is get it from SDK-man. We always highly recommend SDK-man. It's our favorite way of installing JDKs. We love it. And this is the repo that contains all the info, notes, comments, 25 updates, all the demos from this talk. And thank you so much for coming to this talk. I had a lot of fun those 3 hours. I want to still save a bit of time to chat with you and answer any questions you might have. I hope this will be useful for you, and definitely was a lot of fun for me. So thank you so much for coming, and please provide feedback for this talk. Thank you.